Hello and welcome to this video. In this video, we will learn about red-black trees. I had I have covered the basic data structures. I had planned to do a XOR linked list. Starting from my previous video, I'm doing advanced data structures. So XOR linked list and red-black trees, or for example, AVL trees, are part of that. The original plan was to do XOR linked list, but somehow I missed that video, the content of that video, and I ended up finishing Red Black Tree first. So this video is that the result of that work. In the next video, we'll do XOR linked list, then we'll follow it with the AVL trees. Now, red black trees are very important. The reason is it is optimal in terms of the algorithmic complexity and performance. So we know that binary search trees, or the trees which we have studied, the binary search tree, have a problem. The problem is that if the insertion is not good, the tree can get skewed. By skewed, you understand that the number of children on left and right side are not balanced. Red black tree solves that problem. Why skewing is bad is because it will worsen the insertion time, it will worsen the search time, so we don't get the benefit of the binary tree. Now, red black tree is a self-balancing binary tree like AVL tree or splay tree. So the advantage of this balancing nature is performance. The algorithms is little bit involved for insertion and deletion, but it is reasonable. It is not as complicated as AVL tree or split trees. Split trees are fairly complex. Now, why I said it is very important tree is because if you look at GCC's GNU compiler, C++ implementation, then in that they have implemented the map data structure using a red black tree backend. Now, you will say, well, the search would not be O1 anymore. The search would become O log n. The argument behind choosing the red black tree for a map is that when you have a large map, okay, when the number of elements are very high, then there will be collisions. It does not matter what we do, there will be collisions, and you will have to do the collision removal. You will have to sort out the collisions in case of a map. If you use open addressing or closed addressing, whatever way you do, it will come. Now, because of collision, the search time worsens. And if you read the GCC documentation, it says that it worsens to log n. I'll say, okay, what about the small trees? Or small hash maps? If you refer to my hash map video, a better hash map, then you will see that calculating hash is not so simple. It involves a lot of steps to compute a good hash. And for small binary trees, the insertion is fairly simple. Okay. And for small binary trees, number of steps to find an element is far less than computing the entire hash, or executing the hash function is far more complex, and computational power is required. So you see, GCC people are not idiots. They have thought it through, and that's why they chose red black tree as the backend or storage for map. So with that out of picture, let's go through this red black tree. So I have shown a red black tree here. There are black nodes, red nodes. So you see there are only red and black nodes. Let's go through properties of this. These n are leads, that means null. So the properties of red black tree include following items. One is that every node is either red or black, as we have seen. The root node is always black. That was the black node here. Root node is black. Red nodes cannot have red children. Red nodes have black children, as you can see. Okay. all leaves are black nodes. So these leaves are black nodes. Remember, black nodes can have black children, okay? So it doesn't matter if the parent of null nodes or leaves are red or black. The leaves can always be marked as black nodes. Now, fifth property is that every path from a node to its descendant null nodes have the equal number of black nodes. So if you see from here, to leaf, there are two black nodes. Two black nodes, here also two black nodes. So that's the arrangement we have in red black tree. Insert, search, and delete all have the time complexity of log n for red black tree. RBT means red black tree. The black height of an RBT is the number of black nodes on a path from root to a leaf. Leaves are counted as black. So an RBT of height h has black height greater than equal to h by 2. Height of an RBT with n nodes is height less than equal to 2 log of n plus 1 with base 2. The black depth of a node is defined as number of black nodes from the root to that node. So if you observe these rules, particularly rule number 3 and 4, okay, if you observe, or including 2 also, okay, if you observe rule number 2, 3, 4, then you will figure out that a skewed tree of 3 nodes is not possible. It will violate either 3 or 4. Okay. So with this out of picture, let's go through insertion. Now, when we insert a node in red black tree, the insertion occurs as if it's a binary search tree. That is the first step we take. Now, after doing the insertion, we have two possible cases for a node. Uncle is red. Now, if uncle is red, we recolor the parent and uncle to black and grandparent to red. Then we move up the tree to correct the violations. If uncle is black, then there are two subcases. Node is a right child, then you perform a left rotation on the parent. Node is a left child, then we perform a right rotation on the grandparent and recolor. Similarly, when we delete, we can have a problem of double black. So this requires fixing. Now to fix this, we check the sibling. If sibling is red, rotate the parent and recolor the sibling and parent. If sibling is black, we have two cases, two subcases. Siblings children are black, recolor the sibling and propagate the double black upwards. Now, if one of siblings children is black, then there are two cases. If siblings far child is red, then perform a rotation of parent and sibling and we recolor them. If siblings near child is black, then we rotate the sibling and its child and proceed as above. So if you remember these basic rules, which we have covered till now, you should be able to implement a red black tree. Now, it can be somewhat involving compared to binary search tree, but with a bit of effort, you can get the code right. Now, code is secondary. The primary thing is the theory behind it. So we have an implementation of red black tree here. It has come from the algorithms from GitHub. So we go through this. Now we have certain declarations here. We have a node of which includes several member variables. We have a val. We need parent. We need left and right, which are children, and we have a color. Now, color is an integer, 0 means black and 1 means red. A better thing would have been to declare an enum where 0 could be black, and so you could do something like this. Enum, you can say black, comma red, or better in capital. And then we could say that this is red. It is much better. Okay, but it is not done. So the code is in the repository, the usual place where I put my code. The link will be in descriptions. So let's go through this code and see how it works out. I will not go through all of it, but some of it. So first we go to main function. So we create the root node and we have a menu We have 1, 2, 3, and 0 for input delete in order traversal and quitting. So first is 1 for insertion. Now if root is null, we create a new node and make it black here, and then that's it. But if root is not null, then we call insert node. In case of 2, we call a delete node, and in case of 3, we print in order. Search is simple, and you can implement it yourself. So let's first look at insert node. Now, before insert node, let's go to new node, because that is what we had done for creating the root element. New node allocates memory for structure node. We assign the value. Parent is parent. In case of root, this will be null, and left and right are null. By default, color is red, and return the create. Since the color is red, by default, we made it black. So let's make it black. Okay. Now let's go to insert. Okay. So in the main, we have insert node. Let's go here. So initially the insertion would be like a BST. So remember that in the main, we have insert node. When we call, we supply root and we supply the value. So we have value, oops, we have the value and root. We have a temporary value buff root where we assign the root. And while this buff root is true, that is not null, we check if it is greater than value. If it is greater than value and its left is not null, then we assign it to left as a left child. We assign value as a left child. Okay. Otherwise, we create the node and we make it its left child. Okay. All right. Here assignment is not happened. I was wrong. We go to the left sub3. Now, if it is not greater, if it is if the value of the node is less than equal to this value, we go to the right node and we do the same thing. Okay. Now, once it is done, we break out of the loop. Remember to break out of the loop after assigning the node. Now, if this node is not a root node, we have to perform a check. Let's see what happens in check. So we go to check node. Now, if the node is root, we don't do anything. It is unnecessary, but all right. We don't need this. Node cannot be null and node parent cannot be null. Okay. Now we receive node, we create a copy of node. Now, if both the node's color and node's parent color is black, then we don't do anything. After that, we find out parent and grandparent. If grandparent is null, then parent is root. Then we just make the parent color, that is root's node 0. Now, if both the children of grandparent are red, then the check is like that. The right and left child of grandparent are not null and the colors are red. You can put it red here. Oops. We can correct this and we can put this. Okay. So if this is the case, we make the color black and grandparent color red and we return. Now, if this is not the case, then what we do is we find great grandparent, and if the parent is the right child of grandparent, and so on, you continue and perform the checks and do the assignments. So the code is there. You can look up in the repository and go through it and try to understand. Me reading the whole code will not make sense because you just can't hold this much code in brain just like that. If I explain this, it will just not work out. I can explain this, but it's too complex for someone to understand in one go. It will take you quite a few iterations to understand this code. Similarly, for delete node, you delete it and finally you perform a check here. Okay. So this is also quite big a check. And there are rotations involved. So going through this code just like that is not going to work out. The theory which I explained is what you should focus on. Remember to code it in such a way that the structure of the tree remains true to the definitions. The definitions are very simple. Root node is black. Red nodes cannot have red children, and all the leaves are black. That's it. No matter what you do, these three rules should hold. As long as these three, for example, there can be a chain of 3 black nodes. Okay. So what is the problem with that? You have to think, what is the problem? The problem is that the number of black nodes from the root to the leaf node is now no longer constant. It varies. So you can't have 3 black nodes just like that. Okay. If you have a skewed tree, at max you can have 2 black nodes in a chain. Okay. So for example, let me tell you this. For example, consider this. We have a root node. Okay, and it has 2 children. Let's say, for example, this, this, and one of the children here is, sorry, the root node is black, so let's call it B. Okay, now this node has a black child, and this node is also black. Okay, now it can have 2 what you call children. For example, this and this. Now these leaves after this can be black. Okay, and the 2 children of this can be black. The leaves can be black. That's a valid tree. But these can be red also. Okay, and leaves are black. This is also a valid tree. So it's not necessary that 2 RBTs with same values will have same structure. The structure may be different, depends how you arrange your nodes. So as long as you maintain your basic ground rule of the 4 properties of red black tree, it is okay. So all this balancing and left rotation and right rotation is for that. I have not shown left rotation and right rotation. The reason is that we have already covered it in when we are balancing the binary tree. I have a video on balancing the binary tree. You can watch that. So with this, I will come to the end of this video, and I'll implore you to go through the code. And if you have questions, further questions, you can ask me in the comment. And don't forget to like and subscribe. And I hope that you have found this video useful. Thanks a lot for watching. Have a nice day.